Hello everyone. So assume that we have a population of size n, right? What do you mean by a population? A population is a collection of numerical values. It may be associated to some practical examples. For example, you can take 700 people and their heights, that is a population, right? Now so you have a population of size n and you choose a sample of size small n, right? Now we call the mean of the population as mu and mean of the sample, we can scale the mean of the sample, we can call it x bar. So this is basically we say as a parameter of a population. This is what we called a sample statistic. Okay. So basically in statistical inference we estimate a statistic, then we estimate the parameter using the statistic. So that particular branch we call estimation theory. So a statistic is a estimator of the parameter. Okay, so these are the basic ideas of statistical inference. We go from a particular to general. That's the idea. Now let us look at what is meant by sampling distribution of mean. So we have a population of n elements and we have taken a sample of small n elements. So the idea is we want to collect all samples of size n. Then how many samples will be there? Because we are selecting small n from capital N, so definitely the total number of samples going to be n choose n, or either way you can write, that's not an issue. Now what is the idea is, let me denote these samples by x1, x2 up to x n choose n. This many samples I have, right? And I denote their means by x1 bar, x2 bar and up to x suffix n bar. So when you calculate the sample means, some of them will be identical, some of them will not be identical, right? Maybe every sample mean can be different. All things are possible. So what I am going to do is, I assume there is or there are k different sample means. Okay, so let it be like this. So x I1, x I2 bar up to x ik bar. These are different, and let the frequency will be f1, f2 and up to fk. So you have a sample mean, unique sample means and corresponding frequency. So these are your means and you have the frequency. So what you got is a table, right? And this table contains sample means and their corresponding frequency is called sampling distribution of mean. Okay. Now what is going to be my claim? That's what I want to stress on. Let the mean of this sampling distribution, let it be mu bar. It will be the mean of the sampling distribution of mean. Then my claim is, and also assume mu is the population mean. I mean, you have the all population here, let of a capital N elements, let the mean of that be mu. Then my claim is very simple, mu bar is equal to mu, right? So I have to prove this. Now what do you, now let me choose the population P is equal to the collection of elements y1 up to yn, because that many elements are there, right? Now as we already denoted, the samples be x1 and up to x sub n choose n, and the corresponding means, let's take it like this only, right? Now what is the mu bar? So mu bar is simply, what is mu first? So mu is simply summation y j divided by capital N, where j is moving up to this. What is mu bar? Mu bar is you add all these sample mean divided by total number of samples. So this is x1 bar plus x2 bar up to x and choose n bar all divided by n choose n. So I have to show that this is actually equal to mu. So how do we do that? So what is x1 bar? So I denote xj bar is equal to summation h, a variable where h is belongs to xj, right? Then so what is here, 1 varies, j varies from up to n choose, this many samples are there. So if you put this in here, this is 1 by n, that is also there. If you put this in mu bar, then mu bar equal to summation h in x1 h plus summation h in x2 h up to summation h in x sub choose n, all divided by this small n here will move to n, because every denominator has n, so you can add the numerator and n will be here along with n choose n. So this is what you get. Now what is the problem is, how do you calculate the numerator here? The problem with the numerator is elements in the first sample may appear elements in the second sample. Elements in the second sample may appear elements in some kth sample, whatever. So that is a problem. So we don't actually know what will the sum will look like. But we can do this by observing one important thing, that if h is an element of the population, right? Suppose h is an element of a population, then how many samples are there exactly? right? That is the idea exactly, which contains H. So H is an element in a population, so you can assume say some y1. Now how many samples are there containing y1? So samples are size n. So just pause and think about this. So our samples are of size n, and in that we need the value h. So it's very easy to construct it, because you fix the value h. Now you have to select n minus 1 elements from where? N or n minus 1? N minus 1, because you already taken h. So you fix the value h, then rest of them you select. How many ways you can select the rest? N minus 1, choose n minus 1. So what you can see here, exactly n minus 1 choose n minus 1 samples containing a particular value of the population. Then the numerator can be easily estimated, because then we can write mu bar equal to, so let's give the values for the population. So y1 is one of the element. So how many times it repeats in the total sum? It repeats n minus 1 choose n minus 1. Similarly y2, similarly how much yn will repeat? N minus 1 choose n minus 1, all divided by n times n choose n. Now you take n minus 1 choose n minus 1 outside, then what you have is y1 up to yn, all divided by n choose n, right? Now let's we have to calculate this, right? So we can just take a is equal to n minus 1 choose n minus 1, and b is equal to n choose n. If we calculate this, this is nothing but n minus 1 factorial divided by c n minus 1 minus of n minus 1 will be n minus 1 minus n plus 1. So this will cancel, what you get is n minus n, right? So you have n minus n factorial times n minus 1 factorial. And what is b? b is simply n factorial divided by n minus n factorial times n factorial. Now you put this a and b to your mu bar. So what is your mu bar? Your mu bar is a by b times summation y over n, right? Now if you put this here, you get n minus 1 factorial divided by n minus n factorial n minus 1 factorial. Then b will be go like a reciprocal. Okay, what is left is summation y by n. Now each capital factorial, okay, we write this. If we first cancel the n minus n factorial, so we remove that first. Then what is left is n minus 1 factorial. So we write n factorial is equal to n into n minus 1 factorial. And below you write n factorial is n minus 1 factorial and summation y by n. Now you cancel all. You cancel this one with this one, and this one with this one, and this one with this one. So what you get, summation y divided by n, that is mu bar, that is mu. So mu bar is equal to mu. So this actually shows that the sample mean is a unbiased estimator for mu, or you simply say the expectation of x bar is equal to mu. That is the idea of, right. So yeah, so we have used a simple combinatorial argument to arrive this conclusion, right. Thank you.